Okay, so now we are going to look at the intersection of three planes. So intersection of three planes kind of go into two categories: consistent intersection and inconsistent intersection. So consistent means that an answer exists. Inconsistent means that no answer exists. So we're going to start off with the consistent scenarios. So the very first one is the intersection of three planes to give us a point. So the way that I think of this is pi 3, so this is the floor. So this would be a wall, and this could be a wall. So there's one point that all three of these planes have in common, and it's this point down here in the corner where they all meet. So three planes can intersect at a point. Two planes cannot. Two planes can only intersect at a line, whereas three can intersect at a point. Now, having said that, so if we look at case 2, when we're looking at this situation, the intersection is a line. So I think of this like a book, and the line being the spine of the book where all the pages meet, and each of the pages being a plane. So in this case, all three intersect at a line. So in the first scenario, the normals, they're not parallel and they're not coplanar. So that means the normals are all different. They're not multiples of each other. Same thing over here. So the normals, it says they're coplanar. That means that they will represent a plane. They'll all lie in the same plane. However, they're not going to be the same in the expression when we are given the equations. So normals are not multiples. And that's true for both of these scenarios. So these are considered consistent solutions because a unique solution exists, or a solution exists, I should say. Now, when I look at the scenario here, so case 2b as it's labeled, this is exactly what we saw in the first video. So really, even though there are three planes here, there's technically only two. So these are scalar multiples, the whole thing. So they're the exact same situation. So really, it's the intersection of two planes. You'd only work with two of the planes, not three. And then finally here, this is really one plane. Even though there are three equations, they are all scalar multiples. So in this case, we would have infinite solutions. Okay, so let's get to the math to see what this stuff looks like. All right, so determine the intersection of the three planes with these equations. So hopefully you watched the video on elimination of, or solving equations with three variables, because that's what we're going to do here. I have three planes. I have 2, 1, and 6. 3, 4, 3, 1, negative 2, negative 4. These normals are not multiples. So that means I'm going to start with my elimination. So I'm going to choose a variable to eliminate. So I'm deciding to eliminate y. So I'm going to eliminate y from 1 and 2. So in order to do that, I need 4 multiplied by the first one. So I have 8x plus 4y plus 24z, and I'm going to move that 7 over. That's going to equal 28. Pi 2, I'm just going to rewrite that. So I have 3x plus 4y plus 3z equals negative 8. So I'm going to eliminate the 4y's. So 8x minus 3x is 5x. 24 minus 3, so I have plus 21z equals 28 minus negative 8 will be 36. So I eliminated y from 1 and 2. Now I'm going to do the same thing. I'm going to eliminate y from 1 and 3. You could do 2 and 3 if you want. I'm choosing 1 and 3. So I'm going to multiply the first one by 2. So I get 4x plus 2y plus 12z equals 14, because I'm moving it over. I'm going to leave pi 3 as is. So I have x minus 2y minus 4z equals 9. So this time I'm going to add these equations. So 4x plus x gives me 5x. 2y minus 2y goes away. 12z plus negative 4z, so I have plus 8z equals 14 plus negative 9. So that is going to give me 5. And I just made a mistake. So this here, it's not going to be 5 because that's not negative 9. It's just my bad handwriting. This here is going to be 14 plus 9 is 23. So I'm going to call this equation right here equation 4 and this equation 5. So at this point, this is actually the point where what type of intersection is going to be revealed for every situation, whether it's a point, it's a line, it represents no solution. So if I look at it, these equations are not the same. The x is the same, which makes my life easier. However, they're not the same equation. So that means I have a point. So I'm looking for a point of intersection. So my next step, so I'm going to eliminate x from 4 and 5. So I have 5x plus 21z equals 36. Now this one worked out nicely since the x's are already the same, so I didn't have to do any multiplication. So I have to subtract here. So 5x minus 5x is gone. 21 minus 8z is 13z. 36 minus 23 is 13. So z equals 1. So I have my value for z. So now that I have z, the next variable that I can find, so I'm going to sub z equals 1 into 4 or 5, it doesn't matter which one. So I'm going to sub it into 4. So 5 multiplied by 1, oops, wrong variable. Because I know, so it's 5x plus 21 multiplied by 1 equals 36. So 5x equals 15. X has a value of 3. Okay, and then now that I have both of those values, I'm going to sub z equals 1, x equals 3 into 1, 2, or 3. So it doesn't matter which one. I'm just going to pick the first one because it's there. So I have 2 multiplied by 3 plus y. Oh, and actually this one works out best because there's no coefficient in front of the y, so it's a little bit quicker. Plus 6 multiplied by 1 equals 7. So I have 2 times 3 is 6, plus 1. So let me just look at this. So 2 times 3 is 6 plus that. So this is a 6, not a 1. Okay, so that makes more sense. 6 plus 6 is 12. So y is going to equal negative 5. So that means, oops, therefore, there's a point of intersection at 3, 1, not 1, because that's the z value. So just be careful down here in the order, because the order needs to be the correct coordinate. So 3, negative 5, and 1. You can actually check your answer, which is nice. You can sub it into all 3 equations, and the left side should equal the right side. All right, so next scenario here. So we have 1, negative 5, 2, 1, 7, negative 2, 8, 5, 1. All right, so in this situation, the normals are not multiples. So that means I might have a line or a point. So let's go ahead and start our process. So I'm going to eliminate z from 1 and 2. I'm going to write that x minus 5y plus 2z equals, I'm going to move that 10 over, x plus 7y minus 2z equals negative 6. So when I do that, the z's are opposite signs, so I'm going to add them to make them 0. So x plus x is 2x. Negative 5y plus 7y is going to be plus 2y equals 10 plus negative 6 is going to give me 4. I can reduce this. Should you reduce? Yes, because then it's sometimes easier to see scalar multiples. So I have x plus y equals 2. Now, same process, so I'm going to eliminate z from, let's do 2 and 3. So pi 2 is fine. So I have x plus 7y minus 2z equals negative 6. But I'm going to multiply 3 by 2. So I get 16x plus 10y plus 2z equals 40. Okay, so when I do this here, the z goes away, so I'm going to add. So x plus 16x is 17x. 7 plus 10y is plus 17y. Z goes away, and negative 6 plus 40 is 34. So when I reduce this, I'm going to get x plus y equals 2. So this, like I said in the last example, this is going to tell us what type of intersection we have. So because these equations are exactly the same, the intersection has to be a line. So what do we have to do now? Now we have to do what we do for the line. We're going to arbitrarily state what the parameter is. So I'm going to let x equal t. So that's my first parametric equation. So then when x is equal to t, I'm going to have t plus y equals 2. So y is going to equal 2 minus t. So that's my y parametric equation. Now I need to get my x. So I'm going to sub into the first one. So I have x minus 5, but instead of putting y, I'm going to put 2 minus t. Once again, I'm not looking for x. I'm going to be looking for z. So I know what x is. So I have t minus 5 times 2 minus t plus 2z equals 10. So I have t minus 10 plus 5t plus 2z equals 10. So t plus 5t, so I have 6t plus 2z equals 20. 2z will be 20 minus 6t. So z equals 10 plus 3t. So now that means my vector line, or vector equation, x has a position vector 0, y has a position vector 2, z has a position vector of 10, plus t, x is 1, y is negative 1, and z is 3. So that represents the situation when the equation is going to be a line. Okay, and you can tell because this equation and this equation are identical. So when it's a point, they're not the same. When it's a line, they are the exact same. Okay, so now the next part deals with inconsistent solutions. So these ones here, there is no solution because all three planes are not having contact with the same place at the same time. So our first one, you can see, they're all parallel. So the normals are the same, but the d values are not. Multiples. So there's no solution. Case 2, we have two planes that are parallel, and the third one intersects both of them. So as pairs, there's a line of intersection, but as all three of them together, there's no solution. So two sets of normals are multiples. Now case 4, I'm going to skip case 1 for a second there. So case 4, so these planes are the same. So the normals, or they're not even normals, they're scalar multiples. And then this here would have a different d. Now the last situation that's here, this is what we call the triangular prism. So when we're working with this, the normals are not multiples. So already in this lesson, we have when the normals are not multiples, we could have a point, we could have a line. So this is a third possibility. And once again, the nature of the intersection is going to come out when we do that first elimination step. So really, by looking at the normals, we're narrowing down the possibilities. We don't necessarily know what the answer is until we start manipulating the numbers. Okay, so determine if each system can be solved, then solve the system or describe it. Okay, so I'm looking at this here. So I see 3, 1, negative 2, 1, negative 5, 1, 12, 4, negative 8. So I'm going to have a look at this here. So I have 3x plus y. So the first equation and the fourth equation, they have normals that are multiples. So I'm going to multiply this equation here by 4. So when I do that, I get 12x plus 4y minus 8z equals 48. So the number I'm interested in is this value right here. So this tells me I have two parallel planes intersected by a third. Therefore, there's no solution because all three planes are not in the same location at the same time. Okay, so here we have 1, 3, negative 1, 2, 1, 1, 1, negative 2, negative 2. So these are not multiples. So I'm going to start by eliminating. I'm going to choose to eliminate x. You could choose to eliminate any other variable. I'm just choosing x. So I'm going to start off with 1 and 3. So I have x plus 3y minus z equals negative 10. X minus 2y plus 2z equals negative 4. So when I eliminate, x, oops, it won't be a plus because the x's are the same. So I have to subtract. So x minus x goes away. 3 minus negative 2 is 5y. Negative z minus 2z is negative 3z. And negative 10 minus negative 4 is going to be negative 6. So that was my first elimination of x. Now I'm going to do the same thing. I'm going to do 1 and 2 this time. So I need 2 pi 1. So I have 2x plus 6y minus 2z equals negative 20. Rewrite pi 2. So 2x plus y plus z equals 8. So again, I'm going to subtract. 2x subtract 2x goes away. 6y minus y is 5y. Negative 2z minus z is minus 3z. And negative 20 minus 8 is going to be negative 28. So our coefficients are the same. So 5, negative 3, 5, negative 3. But the d values are not. So this means we have the triangular prism. So they intersect at a line in pairs, but not all three. So therefore, no solution. Okay, so in this case, so another, like I said, another way that we can do this, so I'm just going to state the normals. So normal 1 is 4, negative 2, 6, and my d is 35. Normal 2 is equal to negative 10, 5, negative 15, and d is equal to 20. Normal 3 is equal to 6, negative 3, 9, and d is equal to negative 50. It's a 5, not a 3. All right, so if I reduce everything, so down to the lowest terms, I'm going to divide out a 2 here. So I'll have 2, negative 1, and 3. So what I do there, I need to do here. So 35 over 2. I'm going to divide by negative 5 right here. So I get 2, negative 1, 3. And I have 10. When I do, oh, not 10, sorry. 20 divided by negative 5 is going to be negative 4. and then I'm going to divide by 3, or yep, 3 works. So I have 2, -1 and 3, and -50 over 3. So for this situation, there is no solution since 3 parallel planes. So doing that little analysis of the normals and the d-values in the beginning can definitely help cut down the amount of work. Since in this case, if you'd gone ahead and done the elimination, you would have got a bunch of equations that were the same. All right, so hopefully that makes sense. Again, it's all about manipulating those equations and eliminating variables.